All right. Welcome to another episode of the PyTorch Compiler series. Today we have Sayak Paul from Hugging Face and also Animesh from the compiler team. And Sayak is going to talk about how to achieve peak performance on diffusers with Torch Compile. And if time permits, we can get into ahead of time compilation as well. Take it away, Sayak.
Yeah, thanks for the introduction, and also thanks for agreeing to do this. I've been catching up with some of the episodes of the PyTorch podcast, and I think they have been very informative and educational so far. I think they are developer friendly. And yeah, I'm really glad to be here today. I always cherish the collaborations that we have had in the past, and also the ongoing collaborations, especially with the compile team, Animesh, Ryan, and so on. So yeah, looking forward to it.
All right.
Yeah, is there anything else?
No, no. I mean,
I should,
you can go ahead. Yeah.
yeah,
You share your screen and yeah.
cool. Uh, I hope, yeah, the screen is visible. So,
Yeah.
so uh, I think the contents of the stuff will be made will be accompanied with the video that's gonna get released, like the link to the blog post. So I hope I won't have to pop over the link on the screen or somewhere. Is that about
Yeah.
okay?
Sounds good.
Yeah, yeah, yeah. Okay. Um, so yeah, this is a fairly recent blog post that we did. As we can see, this is a collaborative effort between myself, Animesh, and also Benjamin, who is not present in this call. And before I dive deeper, I think I should introduce diffusers a bit. So diffusers is a Python library for state-of-the-art video, image, and audio generation, and you can probably also get a little bit of a cue that's hidden inside the name diffusers. Diffusers is entirely based on diffusion and flow-based models. For the context of this call, we do not have to know what diffusion or flow-based models are. But know that diffusers is very similar to the transformers library from Hugging Face in many spirits, but it also has many different parts. So yeah, that's like a one-liner introduction to diffusers. So if you are looking for use cases around image, video, or audio generation, you might want to check this out. And this blog post is basically about how diffusers embraces everything there's to embrace from Torch Compile, how we try to make the library very Torch Compile friendly, and also how we try to ensure you get all the performance benefits from Torch Compile right off the bat. So this post basically goes over all the different aspects of performance that you can get if you use Torch Compile with diffusers. And also it covers many realistic scenarios such as offloading, LoRA, quantization, and so on. So yeah, and as you may have already noticed, this is a very hands-on guide. So there will be code, there will be numbers, and so on. So first and foremost, if you prefer using Torch Compile, I think you would probably want to ensure a few things within the model to ensure that Torch Compile is giving you the most amount of benefits right off the bat. And Animesh and Avik, you can please and you can interrupt me if I'm going wrong somewhere.
Yeah,
But
sure.
from my understanding, these are like the two most essential thing that a developer needs to really care about, that your model does not have any graph break and your model is not leading to any recompilations when you are applying torch compile on it. So if you are writing your model implementation in that way, I think you are already kind of set up for success as far as performance boosts from torch compile is concerned. And then, as I was mentioning at the beginning, we will also cover a few real world use cases and so on.
Yeah,
So
maybe
yeah.
it's worth noting a little bit that, yeah, I mean, traditionally Torch compile is a JIT compiler and it can tolerate graph breaks, but this is a good direction that we are kind of all moving in, where we're trying to apply full graph equal to true wherever we can. And a lot of our upcoming technologies are also kind of starting to assume that you don't have graph breaks, you put in a little bit of effort to not have graph breaks, and then you get outsized benefits.
Yeah.
Yeah,
But one
indeed.
more thing, but one more thing I
Yeah.
want to add here is that so like when so we did similar efforts earlier, and one of the challenges used to be where should we apply torch compile? Because applying torch compile at the very top usually leads to graph breaks, and this led to a bad user experience. The one of the main reasons we went with Diffusers collaboration is to actually figure out where exactly torch compile should be applied. And once you know your model architecture, you very well know, oh, this is the part which is computationally expensive, and this is the part where torch compile will be useful. And once you have narrowed down to that part, usually the things like full graph equals true and recompilations are way easier to reason than applying it on the full torch compile on the full model. So I think in this case, for diffusion models, we find out, okay, which part of this diffusion model is actually compile friendly, and then we apply there, and it's way easier to reason about these properties there.
Yeah, indeed. And sometimes the problem is since like rotary positional embeddings are a very crucial part and they often make use of complex numbers. And if you use torch compile, you would probably already notice. And this is of course not for you to a week and Animesh. This is for the developers out there who
Yeah,
make
yeah.
use of torch compile. Is like if you are using complex numbers too much, you get spit right at the face that probably the eco performance is gonna be better. So it made a lot of sense to try to figure out regions or let's say parts within the model that are torch compile friendly, and then benchmarking that and then taking things forward as Animesh mentioned. And also I think it's a good idea to mention that having too many graph breaks can lead to a fragmented graph, and like fragmented graphs are not really a good thing. You are essentially aiming for a nice dense graph where there are as little fragments as possible. So full graph equals true is a like very reasonable and effective starting point, I would like to mention as a developer myself. So that's one bit. And then we in our journey to figure out and also to reason which parts or which regions within the model are torch compile friendly, Animesh came up with this thing called regional compilation,
Mhm.
which is like taking the repeated blocks within your model. For example, let's say in your language model, you will typically have identical transformer block, which you would sort of repeat for many layers, let's say 19 layers or 20 layers or even 50, 60 layers. So these these layers, they share identical structure, which are sort of stacked on top of each other. And in regional compilation, you typically take these, identical blocks and only compile them. And in our experiments, we found out that regional compilation gives almost similar speed benefits, but it cuts down the initial compilation time up to 10x. Of course, it depends on the model itself, but on an average, we saw like at least 8 to 10x reduction in the initial compilation time, which is like a huge boost in developer experience. And I'm saying this from my own experience of working with torch compile, both full model compilation and also regional compilation. We will get to the numbers that will make things clear already, but I wanted to also give you a bit of a teaser as to what regional compilation can do. Animesh, maybe you have something more to add?
Yeah, so one thing I want to sort of mention here is that this concept where should we apply torch compile is sort of hierarchical, if you may. In a sense, like for example, for the diffusion models, there are many parts of your model. I'm not an expert, but it is like things like before you get some, you do some like convert it, your prompt into some numbers, and then there's a noisy tensor which goes into a diffusion model, and then there's like a decoder at the end. So even at that level, you first have to figure out where to apply torch compile. And once you have figured out, okay, like this diffusion model is the most time consuming thing, then you say, okay, in this diffusion model, what is the best way to apply torch compile? If you have sort of figured out this thing very nicely, you are set up for torch compile compatibility. So what Sayak said is like, even if you have figured out diffusion model is good, maybe going inside diffusion model, figuring out, oh, there are these transformer layers which are repeated, and you can apply compile there is sort of a good insight to have, which will make sure that you have the best cross compile experience. Sayak.
Yeah, yeah, indeed. Like I was about to also go through this part, but it's an extremely crucial point. Unlike many language models, diffusion models are not single models. They are never really single models. It's like it should be written in caps, really. So as we have written in the blog post itself, the Flux, which is a fairly well performing open image generation model, it has got like two text encoders. It has got the denoiser, which is like a diffusion transformer architecture, and then you have got a decoder from a variational autoencoder. Now, amongst four of these models, the denoiser, as Animesh rightfully mentioned, is the most compute intensive component amongst all the four models that we have. So decoding, it's just one time. The text embedding, it's also just one time. But the denoiser, it's invoked over a period of, let's say, 30 iterations or 50 iterations. So it's exactly where most of the compute is spent on as far as diffusion is concerned. And it's a very good rule of thumb to only apply torch compile to the most like compute intensive component as far as diffusion models are concerned. And just for the record, I'm going to be using flow based models and diffusion models quite interchangeably. I know they differ in many ways, but uh, just for the sake of this conversation, I'm gonna be interchangeably using them. Now, as I was mentioning, it's a reasonable starting point to only target the most compute intensive component within the whole diffusion workflow, which is almost always the denoiser, and then sort of take things from there. So yeah, so that's one. And we of course have got like full blown test suits checking if an architecture has any graph breaks, if an architecture is leading to any recompilation problems unless explicitly otherwise specified, and so on. So I think, as I was mentioning, also in my own experience, if you can ensure your model can be compiled in a full graph manner, and also it doesn't have too many recompilations, at least if ideally there shouldn't be any recompilation, but for some reason maybe your model has got 2 3 recompilation triggers, it's already set up for success. Like almost always it's gonna lead to like a fairly sized speed up, I would like to say. But there are other things as well, like figuring out which component in the whole diffusion workflow to target torch compile for. That's one bit. And then you also try to figure out the regions, the repeated regions, so-called repeated regions within your denoiser to only compile those. That's all good and fair. But here's also a small catch. When you are using torch compile in the full context of the diffusion workflow, there also might be some device to host syncs, which can also slow down or let's say get in the way of your fullest optimal torch compile experience. So getting rid of device to host syncs can also be beneficial. I just wanted to call that out, and we try to ensure our diffusion pipelines do not contain those things, so that so that you are so that they are not getting in the way of optimal performance as far as torch compile is concerned. So yeah, any questions up to this point? Regional compilation, host transfers, and so on.
We skipped over the dynamic shapes part, but we can come back to it later.
Yeah, I wanted to come back to
Yeah, yeah,
the dynamicism a bit later.
yeah.
So that's one bit, and I think it's also a very good experience to also try to go over the code a bit, because I've been mentioning how complex the diffusion workflow can be, how it involves like 3-4 models and so on. Maybe the code would look ugly, but it's just a few lines of code, really. So if you have ever used transformers, it's very similar in as far as programming constructs are concerned. You still use the from pre-trained API. You use a prompt to generate your image. For example, we are using here the Flux image generation model, and voila, you are already started in no time. Now enabling compile is just one line of code, so it's just basically that, and you pass full graph through to ensure the full graph is compiled. So yeah, we from our experience, as we can also see, it cuts down the latency on an H100 from 6.7 seconds to 4.5 seconds, which is like 1.5x speed up instantly, just with one line of code, which is really cool. And of course, as a result of that, we recommend the model authors to use full graph equals to sort of try to see early on if your model has any graph breaks. Like you are done implementing your model. Now maybe you have some performance aspects in mind that you want to sort of knock off right off the bat. After, as soon as you are done implementing your model, you might want to just test that implementation with compile full graph equals true and see if there are any graph breaks. I think it's a really good way to approach some of these optimizations.
Well, very quickly on graph breaks, Animesh, we're going to have some material on how to deal with graph breaks soon, right? William was working on something.
Yeah, so we have a graph break website, and we also have a programming model doc. So yeah,
Cool.
that's
Yeah, yeah, yeah.
Cool. Yeah, maybe when the video comes out, we could sort of include all the links in the description of the video. So it's gonna be beneficial for me as well. So I'm looking forward to those. And one big elephant so far has been regional compilation. And if you were wondering how complicated the whole graph traversal might be within the model to find out, hey, these are my identical blocks, and then I'll have to apply compilation to those only. If you were worried about that recursive traversal of model graphs, it's also, again, just one line of code, thanks to Animesh, who contributed this compile repeated blocks API within Diffusers. So instead of doing transformer.compile, you do transformer.compile underscores repeated underscore blocks. So yeah, I mean, it's just that one line of code, and it also cuts down the latency quite a bit. I'm sure there's a mistake. It should have been 6.74 seconds, not 67.4 seconds. We can correct that. Sorry.
This is compile time latency.
This is the compile time. Sorry about that. So when you are doing I should mention this. So when you are doing transformers.compile, this is the full graph compilation. There's no regional compilation involved here, and the initial cold start timing for this is 67.4 seconds. You will have to wait about a minute to start seeing the speed benefits. But with regional compilation, we cut that time by 7x, while still delivering the 1.5x runtime speed up. I mean, why would you not use this? My question to the fellow developers is, why would you not use regional compilation unless you are getting some like 1.7x speed up compared to 1.5x speed up? So one, you get a really significantly more enhanced developer experience. As you can see, you no longer have to eat popcorn while your model is compiling, and you are also getting the similar speed benefits. So if, like, as I was mentioning, if you were worried about the complicated API, it's not complicated at all. And we also provide some description within the blog post itself to enable any model implementation within diffusers if it's not already regional compilation friendly, and it's also fairly easy to enable that in case it's not already supported. Animesh, you had any more points to add?
No, I think you covered it.
Yeah,
Yeah.
I just on a technical level, I had a clarifying question. So the reason you want to apply regional compilation is that if you didn't, then the same block would be sort of unrolled multiple times and creating a larger graph, and that would cause the compilation overhead. Is that right, Animesh? And instead we managed to reuse the same graph.
Yes,
So
that is right. So compilation time is not is greater than ON. We don't know what really it is, where N is the number of nodes, number of ops in the graph. So regional compile is just basically cut the N part. Yeah.
Yeah. Yeah. And also one quick note here is that many developers tend, especially when it comes to benchmarking, many of them forget to clear the compilation cache, and then they start seeing like better cold starts once they start reusing the cache. And in our benchmarking, we did ensure that we are clearing all the compilations cache, and we are always starting with a fresh inductor instance. This is very, very important when you are benchmarking these things. Extremely important. So yeah, and we provide all the code to do it. So don't worry about the code. It's all there in the blog post itself. Now, when it comes to like image generation models or video generation models, we want to be able to have the flexibility of generating images of different resolutions. Maybe you prefer portrait mode, maybe you prefer landscape mode. Depending on your preference, the resolution can also change. It's not just about that square 1024 by 1024 resolution, right? Maybe you have an even higher resolution in mind, or maybe you want to go for something like 1768 by, I don't know, 768, and so on. Now, if you are compiling for a particular shape, and if you are not doing it with dynamic compilation, which is we are doing with dynamic equals true, it's gonna error. It's gonna error out. Like without that flag turned on, and there are some other recommendations from the PyTorch team as far as enabling dynamic compilation is concerned. But within diffusers, we just simply pass dynamic equals true to enable compilation for those use cases where users would typically want to use more than one resolutions in which the compilation was initially performed. But there are other recommendations from the PyTorch team itself where they suggest the use of mark dynamic. Maybe Animesh, you want to quickly
Yeah.
go over that?
Yeah. So a little bit context about dynamism in torch compile. So by default, when torch compile runs, the first run it assumes static shapes. So all the tensors, when we put guards, and there's like a blog on guards if you want to know more details. But whenever torch compile specializes a graph, it for the first time it assumes that the tensor shapes will all be static. But in this case, for example, as Sayak said, you might want to have different heights and width of the image, given you want landscape or portrait and all those kind of things. And therefore, when you ask for a different height or width, there's going to be a recompilation. And this recompilation means that at runtime, you will again see a compilation cost, even though with regional compile it might be 10 seconds, but still there will be an in the middle of your run, you will see a compile time cost. To avoid that, we can use dynamic equals true, which means that all the when torch compile is adding guards, it will assume that the tensors will have dynamic shapes. Um, there's a catch here. Torch compile team does not recommend dynamic equals true because when you use dynamic equals true, all the tensors in your model are assumed to be dynamic, which means you are introducing a lot of dynamism into your model. And when you have a lot of dynamism, the generated GPU code might not be the most optimal. So what you really want is to have only that part of your model dynamic, which has to be dynamic, while the rest of the model can still be static. Um, so, so for that, PyTorch recommends Mark Dynamic. And it's unfortunate that we were not able to quickly figure out what needs to be done. I think there is some UX uh, ergonomics that we have to improve around dynamism. Um, in the case of diffusers, dynamic equals to works very well, and therefore that's what we went for. Um, yeah,
Yeah, to be clear, mark dynamic basically means that you have to identify which tensors, input tensors, and which dimensions you want to be dynamic. So that gives you more control, but it's also like you have to know more about the model and so on. Yeah.
yes,
I will take a few homeworks for myself from this conversation. Is I will try to do, let's say, I will try to not use dynamic equals true when doing it on Flux. I'll try to understand the log, compilation log. It's gonna error out. I'll try to understand that log, and I'll only try to apply mark dynamic to the tensors or the modules where it is applicable, and then I'll try to benchmark it and see if there's any improvement in the compilation time, or maybe there's an improvement in the overall latency and so on, and then I can pass this feedback to you guys, and we can figure something out. It's not like everything is set in stone, we can't ever use mark dynamic. It's not like that. And since we of course use like is torch compiling and stuff like that, we already know that we have the user dependencies figured out, so
Yeah.
that's not going to be a problem. And then I'll also try to see if I can come up with some user level suggestions, like if there's a utility that could suggest better to the users, hey, probably these parts within your graph need to be marked with mark dynamic, and please go ahead and investigate more, something like that.
Yeah.
So I think that could be something that the PyTorch team could work on. And on my side, as a user of Torch Compile and an optimization nerd, I can try to figure out if mark dynamics is actually better for us than using dynamic equals true.
Yeah, yeah.
Yeah.
So if your conjecture is like, okay, the image sizes are to be dynamic, maybe batch size sometimes is dynamic, and so those would be the usual suspects you first make dynamic. But at the end of the day, you might be right. Like the observation could be that it doesn't matter for diffuser models that
Yeah.
everything is dynamic versus specific, because essentially dynamic equals true is what you would like convert it to during this.
Yeah, yeah, indeed. I think even like having a short note or short guide somewhere that, hey, we have like taken top 5 models, and these are our observations about using mark dynamic and dynamic equals true, and giving numbers from all the, I don't know, A100, H100, and I don't know, A10 maybe. And then it can be a very good resource to just maintain and just to refer to, So I'll do that. I'll make a to-do of this, and I'll get back to you. Yeah, I think we have spent a bit of a time going through all the basic compilation related use cases, and also definitely not basic regional compilation, basic in terms of how you would use it in diffusers, but the concept is very interesting, and also the kind of speed and cold start time benefit trade-off that you get is significant. But the diffusion community in general, it also has many constraints. Like, we are assuming we have access to an H100, but many users in the community may not have it. It's pretty expensive. So what about consumer friendly GPUs, and so on? And then how does this whole torch compile thing play out with LoRa adapters, for example? And the reason why LoRa adapters are interesting, because LoRa, when you inject a model architecture with a LoRa adapter, the architecture basically changes. You are essentially injecting extra layers into the model. So you are compiling for one architecture, and then when you are injecting LoRa's into that model, you are essentially changing that architecture. So recompilations are bound to happen. And in the blog post, we go over the solution that we take to enable torch compile benefits when dealing with LoRa adapters and so on. And there are like different exotic forms of offloading, which I'm not going to go over for the interest of time. But essentially, we try to also make sure compile works and gives you a very good trade-off between time as in the runtime, the speed, and also memory. So we try to strike a good balance between memory and time as far as offloading with compilation is concerned. And all of the minute details are in the blog post. But again, like enabling offloading, enabling compilation with offloading is all very simple. It's all very like intuitive. It's all exposed via very intuitive APIs, if I may. So yeah, so that's one bit. That's one. Offloading is one way to go about reducing memory. But quantization is also a very popular way to reducing memory if you can achieve some loss in the quality of the outputs. But in oftentimes users are unable to sort of distinguish between a non-quantized output and a quantized output. So I'll show you. Like on the right hand side, we have the NF4 quantized output, and the left hand side we have got the BrainFloat 16 the output. So for the same prompt and for the exact same model inputs. So you might have a question like, when I'm using quantization, can I still retain torch compile benefits? In other ways, you would ask, hey, let's say I have quantized my model. Now I want to apply torch compile on it and see if there are any speed benefits. So of course there is. In this case as well, we are getting 1.5x speed up. Like without torch compile, it's about 7.279, and with torch compile, it's 4.08. 4.048, 5.04. Sorry, I'm spelling wrong numbers. But yeah, I mean, if you have memory problems, maybe try with offloading first. If you still have memory problems, then go with quantization. Now you have figured out the memory bit, and you can always combine quantization with offloading if you want to go the step further. Now, once you have figured out the memory bit, maybe you want to squeeze out maximum performance benefits as far as latency is concerned, and then try to apply torch compile and see what happens. Because within diffusers, we have also test suits checking if this combination works. If let's say you have applied quantization, you have applied offloading, and then you are trying to compile it, we test for it to check for compatibilities and so on. And we also try to check if there's any recompilation problems and things like that. So yeah, I mean, this is definitely one of my favorite things within the diffusers library. Of course, there's a maintainer bias when I say that, but I think it enables a whole lot of different use cases, even on a consumer friendly GPU, which is really delightful to see. So yeah.
One question here. So I think people might be like, the audience might be wondering, how do we get the kernels for the 4-bit quantization? So what do you use?
So there are different quantization backends within diffusers. Sorry, I should have mentioned it. So NF4 comes from bits and bytes, and the kernels are shipped from the library itself. But we also have torch.io as one of the quantization backends. So let's say your GPU has support for FP8, for example, 4090, for example, has FP8 support. So you might want to as well use torch.io. So torch.io is another quantization backend that we have within diffusers, and of course torch.io ships the kernels as far as these exotic types as FP8 is concerned. We also have other quantization backends as well, such as GGUF and Quanto, and all the respective kernels that Animesh asked for, quantization kernels, come from these different quantization backends. So yeah.
Okay, and these kernels are compatible with Torch compile because we don't have
GGUF,
that. Yeah.
yes. GGUF is compatible with Torch compile. Torch is of course compatible with Torch compile without doing any without doing any graph breaks. And bits and bytes in its latest versions, it's also compatible with Torch compile with full graph. So yeah, yeah. And if in case anyone's wondering, we do have test suits for this, so don't worry. These features are well tested. And um, at somewhat end of the blog post, you would see this figure, which Animesh has very patiently designed from my incomprehensible logs. So this is good, and we try to get your attention to the highlighted bits as to where you know where regional compilation really shines across different settings like quantization, offloading plus quantization, and of course in the vanilla bfloat 16 data type. So yeah, all of this is exciting, I would say, because I think memory consumption is a real struggle, even for me. Having access to H100, I still struggle with memory optimization. Ohms are far more common to see in the diffusion world, especially with these video generation models, which are not only the models are getting larger, but the sheer space of the representation dimensionality is also pretty huge. So memory is a genuine challenge. And then on top of that, you have that compute bound regime in which the diffusion models typically operate, unlike language models. Now, I wanted to quickly touch upon the LoRa adapter thing. As I was mentioning at the beginning, is that you have your model architecture, then you might have fine-tuned some LoRa adapters on top of that model on your downstream use case. And for some context, LoRa is like an extremely powerful and popular fine-tuning method, which is based on adapters. Instead of fully fine-tuning the model, you just train a bunch of low rank matrices, and then you inject those low rank matrices in your model architecture, and then you perform inference. So instead of doing full fine tuning, which can be really memory intensive depending on the model architecture, LoRa cuts down many memory requirements. So yeah. Now, as I was mentioning a while ago, you have your original model architecture, and then you are injecting LoRa adapters to your model architecture. You are fundamentally changing the model architecture. So if you had compiled that initial model architecture, now you have injected a LoRa, it's gonna trigger recompilation. And depending on the size of the adapters that you are injecting, depending on the size of the model itself, recompilation can lead to bad results. So yeah, I mean, how do we deal with these situations? Now, before we discuss some solutions, are there any questions here? Cool. So two things. When you are doing LoRa, there's a rank component involved. Like, what's the rank in which you would want to maintain a down matrix and an upward matrix. So basically, basically a 2D huge dimensional matrix can be decomposed into two lower rank matrices. Now, what's the rank that we are looking for? So that's one bit. And then can we basically resize the ranks of the load adapters that you want to load in a feature in destructive manner, like in a way that would not impact the final image quality, let's say. How could we do that? Because the reason why this is important is because if we can resize the LoRa adapters into into identical ranks, we won't be probably triggering compilation in the first place. So that's our solution. Like you initialize your model, then you call this enable LoRa hot swap API with the maximum LoRa rank that you are anticipating for 16, 32. Typical ones are like 48 or 64. Then you inject a LoRa adapter, and then you call torch compile, and from there on it's gonna compile for that particular rank. And from that point onwards, if you inject any other adapter, it should work. It should not trigger any recompilations. There are, of course, some little gotchas for you to have in mind, but roughly this is how we go about it in the diffusers code base. So yeah, I mean, the fix was simple conceptually, but shipping this was a lot of fun. So yeah.
Nice. Could you go into like this hot swap basically is doing some in place update.
Yeah,
Whether you use hot swap or not, would the shape still stay the same? And is the idea of using hot swap basically trying to avoid triggering some other guards,
yeah,
and
exactly,
that would force you to recompile, but that would be
exactly.
unnecessary in some sense. Okay.
Yeah, exactly. Now another real world use case would be, let's say you have your model and you are basically letting the users explore different kinds of customizations that come with these different LoRa adapters, right? Now they would want to quickly check, hey, maybe this adapter would lead to a model look. No, I don't like this adapter. I want to replace this adapter with adapter B. So in those cases as well, being able to hot swap to not have any effect from the previous adapters that you had in mind, that you had loaded, is ideal. And of course, all of this without having to trigger any kind of recompilation. So yeah. I think, yeah, that's about like all the real world use cases we want to cover within the context of torch compile and diffusers. And as I kept mentioning, we try to operationalize all of this with like thorough, and I would like to call it proper testing. We have got, all of this tested, and we test all of these features nightly on a nightly basis. But we also have benchmarks to catch any regression early on. Maybe in diffusers version 0.33.0, you were getting really good compilation benefits as far as latency is concerned, and maybe in a later version that performance started to regress. So we have got this benchmarks dashboard that helps us figure these things out. So yeah, I think this is also a very helpful resource, not only for me as one of the maintainers of this library, but also maybe the PyTorch team. Hey, maybe
Yeah.
we introduced some operational bug which we might want to fix. But overall, I think that this gives the community a very good sense of the kinds of you know speed benefits they could get with torch compile, and also help us catch any regressions early on. So yeah.
Yeah, along with the user guide work that you do, like basically trying to educate people on how to use Dodge Compare. I think the benchmarking part is a really important part of what you do. Like basically turning this into science and helping us kind of detect when we have kind of done a bad change or something.
Yeah, and also we try to test the most popular models, like Flux. We test Flux, we test Quen, and then we have got LTX, like all the popular models from the community. And we try to really do our best to deliver the best torch compile games out there right off the box. Now, of course, you can squeeze out even more, but you will have to go a little deeper. I mean, the folks wanting to squeeze out more, they will squeeze out more eventually. But for for most of the folks, like doing some simple things can really gain you like significant wins as far as performance is concerned. Yeah.
All right. So yeah, we're at time today almost. Did you want to do another part two on ahead of time later or
Yeah, I think we should do part two, because our ahead of time thing was spot on. I mean, even like more exciting stuff to really talk about as far as ahead of time compilation is concerned. So we should probably do a part two for
Oh,
sure.
cool. This was great, and let's sync offline on what links to add to the description so that people get
Yeah,
nice.
yeah,
Yes. Okay.
sure. All right.
All right.
Thank
But
you.